In this video, we'll talk about the geometry of complex numbers and how we can visualize them. So the notation z equals x plus iy is really suggestive here, in that we can actually plot these numbers in the plane using x, y as their coordinates. So for instance, if I wanted to plot the complex number z equals 1 plus I can do that. I will use the x-axis for my real axis, as when I plot the real part gives me the x-coordinate. And for the y-axis, I'll take the imaginary part. This matches up with the x plus iy we had before, so I'm basically just plotting the point 1, 1 here to give me this complex number. So I go over 1, up 1, and here is where I plot the number 1 plus I. The same goes for any other complex number I want. So say I wanted to plot w is 3 minus 4i. That would be going 3 in the real direction, and then minus 4 in the imaginary direction. So 3 in the real direction this way, and then minus 4 in the imaginary is down 4. That's going to put me somewhere down here. At 3 minus 4 is where I would plot 3 minus 4i. As another example, you can think about what the complex conjugate does in this case. If we look at the number, a complex number down here, say I'm taking z to be minus 2i, which sits down there somewhere. But I was going to take the complex conjugate. Well, if I hit the complex conjugate, I flip the sign on the imaginary part. We're going to change the y-coordinate from minus to plus or plus to minus. So z bar, which should be minus 2 plus 2i, lives up here. So conjugation flips over the x-axis. We can also use polar coordinates to help us view these numbers. Right? These are points in the plane. I can interpret them in polar coordinates. So look at the number 1 plus I again, which we saw was up here. I can interpret this in polar coordinates. So if I do that, I know this is 1 and this is 1 because that's the real imaginary parts. This is square root of 2, and this angle here is pi over 4. This is modeled by the point 1, 1 in Cartesian, or root 2 pi over 4 in polar coordinates. How do polar coordinates factor into writing out our complex numbers? Well, we know our complex numbers of the form x plus iy, but I can replace x and y by their polar coordinate representations. So I'd get something like r cosine theta plus I times r sine theta, or if I want to factor things out, r times cosine theta plus I sine theta, because another way of writing complex numbers. It'll depend on what you're trying to do if you care about this form or the other form more, and what you're trying to do with them. But here's another way you can also write complex numbers. So for this number we had above, this would be written as root 2 cosine pi over 4 plus I sine of pi over 4. And since sine of pi over 4 and cosine are both root 2 over 2, or 1 over root 2, this becomes the same 1 plus I that we had above when I distribute this out. In addition, we notice here that this r is exactly the modulus of our complex number. If you look back at the picture above, that's what it is. It's a distance from the origin. It is square root of x squared plus y squared, which is r, but that's also a definition for the modulus of a complex number. So those are actually the same thing. They come into a row here. Then we need theta, which is the angle from polar coordinates, and we'll see how that relates to things in a little bit. Now I want to plot the complex number 2 minus I in the complex plane, as well as the polar coordinates of this number. Where are we plotting this in the plane? Well, the real part is 2, so I should go 2 to the right for the real part, and I should go 1 down for the imaginary part because that's a negative I. That's going to be the point somewhere around here, at the point 2 minus 1, to represent 2 minus I. Now I want to find the polar coordinates, and we know that to convert to polar coordinates I need the modulus or the radius, and I need the angle theta. So for my modulus, this is just square root of 2 squared plus minus 1 squared, which is root 5, which is also the r that I get from polar coordinates. And then for the theta, I have to figure out the angle here. What I can do is figure out the angle here and use that as a sample angle and then relate that with a negative sign to get what's going on. So for theta, this should be the inverse tangent of y over x, which is inverse tangent of negative 1/2, which you don't have a nice angle for, so it's not a special angle, but that would be the theta you would need to write this in polar coordinates. You could also write this complex number as square root of 5 times cosine of theta plus I sine of theta, where theta is this angle here from above. It's not the nicest form because it's not a special angle, but it gives us a way to represent the number in polar coordinates as well. Let's get at the geometry of complex numbers. The point is, you can represent these numbers in the plane. Because they have two components, x and a y coordinate, we use those x and y as the points we plot in the plane to see what's going on. And we visualize complex numbers this way as well. You can talk about complex curves by graphing these in the plane. Things like that can also be worked out. But in this case, all we're talking about is how do we plot these numbers and how do we view where they are, how they interact with each other in the plane. We'll see in future videos why this is useful to think about. But as of now, the basic idea is you can plot them in the plane, you can draw them, and you can visualize them using both rectangular and polar coordinates.